Okay, so we're going to talk a little bit more about equilibrium constants and how to. So yesterday we talked about basically how to plug in concentrations, how to make ice tables, that sort of thing. Um, we're going to talk a little bit more in depth about some more complicated problems that we can do with this same basic procedure. So we're not really learning a new process here. We're just learning um, new ways to do it when they give us less information, basically. So which doesn't seem like they can give us much less information than we were working with at the end of yesterday, but they can. So the first thing we need to talk about here is the reaction quotient, all right? And this was just confusing to me in high school. So I want to try and help you not be confused by this. Um, there's this thing called Q, and it's calculated the same way as K, but it's different than K. All right? So here's the thing, all right? When you first start a reaction, when you first dump the reactants in, and that instant before they start reacting, there's a certain concentration of both of those, right? Okay? And then it starts reacting, and in an equilibrium reaction, eventually you're going to end up with a set concentration of reactants and products, right? But it's probably going to move in one direction or another. Okay, so in the example that I just gave you, if this is all we're starting with, if we're just putting those two things together, and there is none of the C or the D to begin with, then obviously the reaction is kind of going to go this direction until it gets to equilibrium. Does that make sense? Because the reactants have to form some of the products. And then once we get to equilibrium, then it's going both directions at the same rate, and our concentrations stay constant. Okay, so that's kind of the idea here. Q is calculating these concentrations when it's not at equilibrium, okay, before the reaction reaches equilibrium. Does that kind of make sense? All right, so it's like right when we dump these things in, or maybe just a few seconds after the reaction has started, but it hasn't gotten to equilibrium yet. All right, so we can actually compare the Q to K. If we know the equilibrium constant, we can tell which direction this reaction still needs to go in order to reach equilibrium. Okay, so hopefully that kind of makes sense. We'll take you through an example or two here. Whoops. So notice Q is calculated, like I said, exactly the same way as K is, right? It's the exact same thing. So you've got your concentrations of your products on the top, right, raised to some power, and that's based on the coefficient in front of the products. And then you've got your reactants on the bottom, okay? So again, you calculate Q exactly the same way as you calculate K. The only difference is you calculate Q when the problem makes it very clear that we are not yet at equilibrium, okay? So if the problem says we're not at equilibrium, or the problem says something about, we have to reach equilibrium, or what's going to happen when the reaction reaches equilibrium, that's a hint that we need to use Q, because we're not at equilibrium yet, okay? K is only for reactions that have already reached equilibrium. There's an announcement about orange juice. Was that you? Okay, alright. So, sorry, we just had an announcement about an orange juice spill. Alright, so, what does this even say? So the significance of the reaction quotient, alright, we can actually figure this out. I'm trying to think of a good way to show this. Maybe if I go back to this screen. Let's say that we calculate our Q here, okay? And let's say, just hypothetically, let's say that our Q equals 1 when we calculate it, all right? And let's say that our K, our equilibrium constant for this particular reaction, is actually 0.01, okay? Something like that. So if the Q is 1, okay, at some certain instant in time, this reaction has a reaction quotient of 1. But the equilibrium constant is 0.01. What needs to happen here? Which direction does this reaction need to go in order to get to 0.01. Reactants to products. Okay, so what needs to happen is, so you're saying that this needs to get bigger? Okay, now remember, we've got to go from this to this, right? Okay, so this number actually has to get smaller for us to get to equilibrium. Does that make sense? We're at 1 now when we, divide all of these. We need to get to 0.01. So what that means is, what actually needs to get bigger or increase in concentration is our reactants, right? As this denominator gets bigger, this number is going to get smaller until we get to K. Does that make sense? All right. So if our Q is greater than our K, then the reaction is going to go this way, towards the reactants, okay? It has to get smaller. And in order for it to get smaller, we need more of the reactants, less of the products, okay? If our Q is less than K, so just, reverse this situation. Let's say that our Q is 0.01 and our K is 1, okay? Then in order to get from here to there, now we need more of the products, okay? So then the reaction would have to go this way, all right? So if the Q is, if we end up calculating a Q and we know that our equilibrium constant is actually bigger than that Q that we calculate, that means the reaction has to go this way. We need to form more of the products before this thing's going to reach equilibrium. What if Q is equal to K? We're at equilibrium, okay? So we're already there. So Q equals K, the system is at equilibrium, not the system. If Q is greater than K, then the system's going to shift to the left, okay, to make our reaction quotient smaller until Q equals K. And then if Q is less than K, then the system is going to shift to the right, okay? So again, hopefully that makes sense. Once we show a couple examples of this, I think it'll start to make more sense. All right, so here's an example. At 448 degrees, the equilibrium constant is 51. It's kind of an odd equilibrium constant. By the way, I will explain in class why the equilibrium constant is unitless today. I don't think we have time for that right now, but it's kind of a complicated thing anyway. It has to do with thermodynamics, so we'll talk about that. So this is our equilibrium constant. They're telling it to us. It's 51, okay? It's saying predict how the reaction will proceed to reach equilibrium if we start with 2 times 10 to the negative second moles of HI, 1 times 10 to the negative second moles of H2, and 3 times 10 to the negative second moles of I2 in a 2-liter container. All right. So the main thing that you need to notice about this question, and this is how you're going to know that you need to use Q as opposed to K. It's saying predict how the reaction will proceed to reach equilibrium. Well, what does that tell us? We're not there yet, okay? So we're and then another key word here, if we start with, right? Okay, these are our starting concentrations, not our equilibrium concentrations. So they're giving us they're giving us three amounts here. We have to calculate the concentration, but it shouldn't be that difficult. And then we need to use that to find our Q, all right? So I'm going to, again, I wish I had more room here, but I think we got enough room to do this. So our Q expression for this one, let's just go ahead and write that first. It's going to be the concentration of HI. Do I need to do anything to that? We got to square it because of this coefficient 2, right? So HI squared divided by concentration of H2 times the concentration of I2. Okay? So there's our equilibrium expression, and I mean, sorry, just did that. That is our reaction quotient expression, not our equilibrium expression. We're not at equilibrium yet, okay? So what is the concentration of HI? Let's see if we can just do this in our heads. .01, okay, or 1 times 10 to the negative second, however you want to say that, okay? Because we have a 2-liter container, right? So Moles over liters gives us concentration. So if you take 2.0 times 10 to the negative second divided by 2, that's going to give us 1.0 times 10 to the negative second. Or if you prefer, 0.01. Might be easier. Divided by H2. Now H2 is going to be, let's see, that's 0.01 to start with, right? So it'd be 0.005. Or, you know, if you want to keep it in scientific notation, it'd be 5.0 times 10 to the negative third. Whichever way you prefer to write that. Times the concentration of the I2, which is 1.5 times 10 to the negative second. I'm just keeping it in scientific notation to be consistent here. Alright, so that's going to give us our Q, which again is not K, that's not our equilibrium constant, that's our reaction quotient is what that's called. So 0.01 squared, divide that by 5 times 10 to the negative third, divide that by 5 times 10 to the negative second. I'm getting 1.33 for our Q here. And actually, I guess technically it'd be 1.3 if we're worried about our sig figs. So 1.3 is our reaction quotient. How does our Q compare to K on this one? It's much smaller, right? Okay, so Q is much less than K. So if Q is less than K, in order to make this number get bigger, which number in this expression needs to get bigger? The HI, right? The concentration of the HI needs to increase in order to get us to this 51, okay? So, since Q is less than K, so the reaction is going to, how are they asking this exactly? How the reaction will proceed? Will proceed to the right, or it will make more of the product. Okay, does that make sense? Again, it's, you know, they'll be asking you all these equilibrium type questions, and then all of a sudden they'll throw one in and say, well, what if we start with these concentrations? Which direction does it need to go to get to equilibrium? Okay, and then you're going to have to realize, oh, okay, well, I need to, you know, plug this into my reaction quotient expression, see how my Q compares to K, and that'll tell me which direction it's going to go, or which direction it needs to go. Okay, so that's the idea with Q. All right, now we're going to talk about some solving for equilibrium concentrations when they give you even less information than they were giving you yesterday, okay? So what they might do sometimes is give you the value of the equilibrium constant and then ask you to calculate an equilibrium concentration, but they're not going to give you any of the equilibrium concentrations. Okay, yesterday we were giving you at least one of the equilibrium concentrations, and you could figure out the rest of them based on that using the stoichiometry. Okay, so this is a little bit more tricky. There are a few different ways this type of problem might show up, kind of two major ways, I guess. So first way, you might be asked to solve for an equilibrium amount when you were given other equilibrium amounts, which we already sort of talked about this, okay? And this is not hard. So this is kind of a review of what we did yesterday, except I guess the difference here is they're asking about one of the equilibrium concentrations and they're giving you the K, right? So yesterday we were solving for K when they gave you all the equilibrium amounts. So really the only difference is on these, the only difference is where the variable is, okay? We're just solving for a variable on the right side of the equation instead of solving for the K. So maybe slightly more difficult than solving for K that we were doing yesterday, but it's not that bad. And I just don't have room here. All right, give me a second. I'm sorry. I should get more prepared. I'm going to open up a Smart Notebook file again. Um, okay, so it looks like here that I accidentally split the problem onto two different pages, so sorry about that. But we've got the Haber process happening here. This is a very, very important process in chemistry. I think we've talked about it a couple of times. You're going to see it a lot in the equilibrium chapters just because it's a very important equilibrium reaction where you've got nitrogen and hydrogen in equilibrium with ammonia. Okay? And just industrially, it's a very important process because there are a lot of things that ammonia gets used for, fertilizers and that sort of thing. So it's called the Haber process, and the equilibrium constant at 500 degrees Celsius is 1.45 times 10 to the negative fifth. Okay? And it says in an equilibrium mixture of the three gases at 500, the partial pressure of H2 is 0.928 atmospheres, and that of N2 is 0.432 atmospheres. What is the partial pressure of the NH3 in this equilibrium mixture? Okay, what might be a good first step on this one? Okay, let's just set up the equilibrium expression here, okay? Now notice, they're giving us equilibrium concentrations here, okay? So this is not a Q problem, all right? They're not saying here are our starting concentrations, you know, which directions have to go to get to equilibrium. They're giving us some equilibrium values and then asking us about another equilibrium value. So don't worry about Q on these, okay? This is just a K problem. So our equilibrium expression, if we're just going to write the general expression for this one, it's going to be K equals, well, what's it going to be here? What's on the top of this expression? NH3, okay. So, and I guess I better do this in terms of pressure because it looks like they're giving me atmospheres, right? So we'll say pressure of an H3. Do I need to do anything to that? Need to square it because it's got a coefficient 2 in front of it. And then divide that by the N2 and the H2, right? So the pressure of the N2, and that's just to the first power. And then the pressure of the H2 is to the third power. All right? So there is our equilibrium expression. And we just need to plug some stuff in here, okay? Now this, again, this is different from yesterday because they are giving us the K. All right, the K on this is 1.45 times 10 to the negative fifth. That's supposed to be a 5. And that's equal to, let's see, what are they giving us here? They want to know the partial pressure of the NH3, right? So that's actually what we're solving for here. You can call that X if you want to. It might be easier if we just sort of relabel this. Come on. Relabel this X. And then just remember that X stands for the pressure of the ammonia. Alright, but then they're giving us the partial pressures of the other two. They're giving us the N2 is 0.432 atmospheres. And again, when you plug these into the equilibrium expression, just forget about the units. And the pressure of the H2 is going to be, where is it? 0.928. And that is cubed. Alright? So this is not too difficult to solve, right? I mean, we're just basically using some algebra here, maybe a little bit more complicated algebra than we've used so far. But 1.45 times 10 to the negative fifth, multiply that by the 0.432, and also multiply it by the 0.928 to the third power. And that should give me 5.01 times 10 to the negative sixth, and that's equal to x squared, okay? So everybody with me so far on that? Okay, so then how do I solve for x? Just take the square root of both sides. Okay. Now, technically, in math, when we take the square root of both sides, you get two answers. You get a positive answer and a negative answer, right? The negative answer doesn't make a whole lot of sense in this particular instance because that's going to give us a negative pressure, okay? So we're just going to go with the positive number that we get here. So x is equal to square root of this number, which is 0.0022. Okay. And that is going to give us our pressure of NH3. Well, that's not a very high pressure, is it? So how effective is this process at 500 degrees Celsius if we want to make a bunch of NH3? Not going to be very effective. But let's see if this makes sense. What's the equilibrium constant number for this particular reaction? It's really small, right? Which means what? It means, yeah, essentially there's a lot more of the reactants in this reaction at equilibrium than there are of the products, right? So we would expect this pressure of our NH3 to be a lot lower than the pressure of the reactants. Does that make sense? Okay, so this is a reasonable answer. It looks very small at first glance, definitely, but it works. Okay, next. This is where it gets really fun. This is where we get to use the quadratic formula. So this second one here, you may be asked to solve for all of the equilibrium amounts when given the KEQ and the beginning amounts. We're going to need to use the ice tables and the quadratic equation for these. So, let's see, hang on just one second here. Okay, so we've got our example here. A 1 liter flask is filled with 1 mole of H2 and 2 moles of I2 at 448 degrees Celsius. The value of the equilibrium constant for the reaction is 50.5. What are the partial pressures of H2, I2, and HI in the flask at equilibrium? All right. So, tell you what, it occurred to me just now. Let me just do this. Okay, so there's the problem. Just in case someone's trying to watch the video without the notes, then you'll actually be able to see the problem. And now we'll go back here. Okay. Well, we've got two things here. We've got the equilibrium constant, and we've got a starting concentration of H2 and I2. Okay? So, first thing we're going to have to do here, we are going to have to make an ice table. So let's go ahead and write the reaction. We've got H2 plus I2 yields 2HI. And these are all gases. So again, it's perfectly fine to talk about pressures when we're talking about these. And they're actually asking us for the partial pressures at the end of this thing. Okay? So it would probably be a good idea. We've got a choice here, really. We could either plug in concentrations here for our beginning amounts, or we could plug in pressures. Okay? But since they're asking us for the partial pressures at the end, it's probably a good idea to figure out what our pressures are and do that. Okay? So then we've got our initial change and equilibrium. How are we going to figure out the pressure of the H2 in this particular container? Yeah, we've got a volume, we've got a number of moles, and we've got a temperature, right? So we can use PV equals nRT. We're going to have to do this twice, once for the H2 and once for the I2. Okay, so just put this up here. PV equals nRT. And so for our H2, we have 1 mole of that. So this is a, we're solving for P here, right? So P equals 1 mole times, we want this in atmospheres, so 0.08206, times our temperature, which is 448 Celsius plus 273, 721 Kelvin. Then we divide that by the volume, which is 1. Okay, that's going to give us our pressure of our H2. So 0.8206 times 721, 59. That's a high pressure. I guess that makes sense though, because we're at a very, very high temperature, and that's quite a bit of gas. So 59.2, what are our sig figs here? We got 4 sig figs. Well, 3 sig figs with the temperature, so 59.2. No, don't do that. Scared me. Okay, 59.2 atmospheres. It's our initial pressure for the H2, okay? Now, the only thing that we're changing for the I2, let's not do more work than we have to here. The only thing we're changing for the I2 is that we have 2 moles instead of 1 mole, right? So if you look at our PV equals nRT up here, the only thing that's going to change is that the number we just got is going to be multiplied by 2, okay? So we just multiply that by 2, and we end up with 118. Again, these are fairly ridiculous pressures here, okay? So then, let's try and fill in our table as best as we can here. The problem is saying that we are filling this container up with H2 and I2. So, initially, at the very beginning, what is our pressure for HI? Partial pressure based on HI is 0, right? Because there isn't any in there. These haven't had time to react and form the HI yet, all right? So our initial concentration, our initial pressure of the HI is 0. Okay, so now what? Because in all the problems we did yesterday, they also gave us an equilibrium pressure that helped us to calculate the change that occurred. Yeah, unfortunately. Okay, so we don't know how much these things are changing, but we can relate them to one another, right? So I can say one thing for sure at this point, and that is I know which direction the reaction is going to proceed, right? Which direction is it going to go? Well, it has to go to the right, right? If it goes anywhere, it has to go to the right because there's none of the HI here. So let's say, just to keep this simple, I'm going to say that this increases by 2x. Why am I saying 2x? Okay, because of the stoichiometry, right? So I want to keep this simple. So if this is increasing by 2x, then we can say that the reactants are going down in pressure. And how much are they going down? Just by x, right? Because if you look at the coefficient, there's just a 1 coefficient in front of each of those. So these are going to change by a value of minus x. Okay, so now our equilibrium concentrations, or our equilibrium pressures, become 59.2 minus x, 118 minus x, and 2x. No problem, right? So now we need to plug those into our equilibrium expression, which we actually haven't written yet. So our equilibrium expression for this is going to be the pressure of HI squared over the pressure of H2 times the pressure of I2. And then we just plug this stuff in, okay? So pressure of HI is going to end up, if you plug 2x in here, well, I'll just tell you what, I'll just do this one step at a time. make sure we've got this here. So 2x squared, right? I'm using my equilibrium values here. That's what you have to plug into your equilibrium expression, okay? So we've got 2x squared, and then we've got the pressure of the H2, which is, oh, I forgot what I started with here. I started with the H2, didn't I? Okay, so 59.2 minus x times the pressure of the I2, which is 118 minus x. All right, so now we just start simplifying. This is going to be 4x squared on the top, divided by, and you guys remember how to do this, right? I know, we're bringing in a lot of algebra here. You get to FOIL. You guys learned FOIL, right? First, outer, inner, last. Okay, so we're going to FOIL here. 59.2 times 118. So next time you tell your math teacher this stuff has no application in real life, then, you know, at least it has application in chemistry to some extent. Which some of you may argue that's not exactly real life either, but, you know. 6985.6, I'm going to run out of room here. I'm definitely going to run out of room. Okay, I'm just going to write really small and hopefully I can fit this. So 6985.6, that's our first terms, okay? And then we need to do our outer term, so 15 minus 59.2x. And then our outer, or sorry, our inner terms. Am I spelling FOIL right? Yeah, outer, and then inner, there we go. Minus 118x. And then our last term, so that's going to be plus x squared. Okay, and then we just have to continue simplifying here. So we've got 4x squared over 6985.6. Again, this still is our equal to our KP, which we know. So maybe I should plug that in since we know that. It's our K for this is 50.5. So I'll go ahead and plug that in. Raise this up a little bit here. Okay, so 50.5 equals 4x squared over 6985.6 minus 59.2, no, negative 59.2 minus 118 minus 177.2x plus x squared. Okay, well, how do we go about solving this? Any ideas here? Yeah, but we gotta get it in the right format here, right? Because in order to be able to use the quadratic formula, it's got to be in the ax squared plus bx plus c equals 0 form, all right? So we're gonna have to play around with this some more. This we need to get rid of. It's on the bottom of the fraction, right? So we're going to have to multiply both sides by this, which means we basically distribute 50.5. We multiply that by everything that's inside the parentheses, okay? So 50.5 times 6985.6. These numbers are getting ridiculous. 352,772.8 minus 50.5 times 177.2 minus 8948.6x plus 50.5x squared. And that's all equal to 4x squared. Okay, we're close now. We're very close. So then we have to get, you know, everything on one side and have 0 on the other side, so we just need to subtract 4x from both sides at this point. And then I'm going to rearrange this so that it looks like the axb plus bx plus c thing. So 50.5 minus 46.5 x squared minus 8948.6 times x plus 352,000. Yeah, I'm not real worried about that right now. We'll round at the end. Equals 0. Okay, well, slightly more complicated than the quadratic expressions that you probably see in your algebra class, but there it is, all right? And so this takes the form ax squared plus bx plus c equals 0, okay? And when you have that form, I have it written on the white, that's too far. Nope, put this down first. Is that not working? Oh, here we go. All right, yeah. I hate this thing. All right, so the quadratic formula, and it's gonna do it again. Okay, the quadratic formula, x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. All right. Once again, when we have a square that we're solving for here, we're going to get one value that doesn't make sense in terms of chemistry because it's going to be a negative value. The other one should make sense. All right, so we'll just plug this in. So our x is going to equal negative b. So that's going to be 8948.6 plus or minus the square root of b squared, which is 8948.6 squared, is a huge number. Let's see, 8.01 times 10 to the times 10 to the 7th. Okay, so that's the b squared part minus 4 times a times c. A is 46.5. And C is 352,772.8. Didn't make my square root quite long enough. And then we divide all of that by 2 times 46.5. Almost done, I think. It's going to be okay. I'm going to tell you something in a minute that's going to make you mad. 46.5 times 352,772.8. Alright, so that's the 4AC part. 8.01 times 10 to the 7th minus this answer. Gives us a really big number here. I'm just working all this out. You might want to do this on your own. Then you take the square root of that number. Okay, so what I'm ending up with here, what happened to my extend page thing? Oh, it's down here. X equals 8948.6 plus or minus 3805.8 divided by 2 times 46.5. So glad I'm not doing this in class. Okay. 8948.6 plus 3805.8 divided by 93. So I'm getting x equals about 137, or x equals 55.2. Or 55.3, I guess. Okay, so those are our two possibilities for x. I guess I lied. You might get two positive numbers, but we have to check and see which one of these makes a little more sense in our context. Okay, so our initial, let's go back up here. Our initial pressures were 59.2 and 118, okay? Our equilibrium constant is fairly large, which means there's going to be more of the product, most likely. Oh, okay, and actually, that's not our entire solution here, right? Because that's just our x. Remember, in our equilibrium, the pressure ends up being 2 times x, right? Yeah, no, so that's not that bad, okay? So then, our possibilities here for our equilibrium pressure are either 137 times 2, which gives us 274 atmospheres. That seems a bit high, okay? Or 55.3 times 2 gives us 110.6. That's more in the realm of, I mean, it is high, but it's not even as high as the starting pressure of the I2, okay? So that seems a lot more reasonable. So our equilibrium pressure here is about, if we did everything right in this quadratic, it's about 111 atmospheres, okay? Okay, so you might be wondering to yourself at this point, how in the world am I going to have time to do this on an AP test and do anything else? Okay, so one of the reasons that I take you through this whole process is to help you appreciate the fact that you will never have to do this process on the AP exam. Yeah, I know. Okay, I went to an AP training thing a couple years ago, and they're like, you have to teach the quadratic formula. You have to teach it. And I kind of agree with that. I want to show you what you have to do in some of these situations, because there will be situations where you have to use the quadratic to solve these things. But they will always engineer the problems on the AP exam and on my test, okay, and on my test, that's the important part, where there's another way out, okay? So in other words, when you plug your numbers in, you can do something else to cancel the squared part so that you don't have to do a quadratic formula, okay? And so I'll show you examples of some of those types of AP questions. They'll do that on in class, all right? So yeah, sorry to do that to you, but I wanted you to appreciate the fact that we don't necessarily have to do that anymore, okay? All right. Yeah, I'll let them know that you won't be able to do anything for the rest of the day. Okay, well, so we'll go ahead and end the video there, and we'll see you guys in class. Bye.